Hello everybody, and welcome back to another lecture video. In this lecture video, we're going to be discussing Euler-Bernoulli beams. And this is one of my favorite topics because this is a topic that takes everything that we've previously learned and then combines it together. So as you guys are going to see, we're going to see the stress tensor, we're going to see the strain tensor, and we're even going to utilize the constitutive laws between the stress and the strain tensor. So again, really nice subject because it really ties in everything we've learned together and puts it towards a very useful and practical purpose. All right, so Euler-Bernoulli beams. Let's just do a little introduction. So as you guys know, you guys are all engineers. Beams are a very common topic in engineering. If you've been a mechanical engineer or a chemical engineer, at some point in your engineering career, I guarantee that you've talked about beams. Now, beams are an area of interest because they typically include many things that we need as designers, or if you're just learning about engineering, just very nice things that is good to know. For instance, one of them is the shear force function, and the second one could be a bending moment function. And these are ones that every engineer knows, even if you're, let's say, an electrical engineer, I'm sure that you've heard of shear as well as bending moment. Now, these are the two that are typically taught to engineers way back in their first year of undergrad because they're actually quite simple to analyze, quite simple to figure out what's going on with shear and bending moment. Now, let's say that you become a civil engineer and you get more and more interested in beams. Well, as you guys know, when we're designing beams, it's very important to design for shear and bending moment, but we also have to design for things like deflection. Of course, if you're designing a building and you're designing a floor and it's located on, of course, some beams, but they sag a lot, so there's a lot of deflection, well, the occupants might not be very comfortable. It could be able to withstand the shear and the bending moments, but if it's not very comfortable for the users, well, you don't really have a very good design. So, of course, deflection is something we must also analyze, and this is where things become a little bit tricky. Deflection is not always easy to figure out, and as we're going to see for Euler-Bernoulli beams, with a very nice way in finding these deflections. So to determine these more complex things, such as deflections, stresses, or even the strains of beams, it is very common to utilize Euler-Bernoulli beam assumptions. So people usually list these assumptions differently. Some people lump the assumptions into one, some people spread them out. For me personally, I make it into four basic assumptions. The first one is that the deformations of the beam or whatever you guys want to analyze, they're small, basically, which makes sense because if we're designing, let's say, a civil structure or a building, we want the deflections to be small. If we have large deflections, well, then again, we have bigger problems than just the deflections themselves. We can't design for large deflections. We want the deflections to be small. Therefore, the assumption of small deflections, well, it's perfectly valid. The next one is that the beams are made up of a linear elastic isotropic material. Again, when we're talking about civil engineering materials such as steel or concrete, they are by nature isotropic, so we're good to go. And when we design things for service loads, they're usually kept fairly linear and elastic, so we don't really have a problem there with that assumption either. The third one is that the effective Poisson's ratio are ignored, and we're going to talk about this one more in conjunction with the fourth one, which are that plane sections remain plane. As you guys are going to see when we start deriving these Euler-Bernoulli equations, we're going to use 3 and 4 kind of together to figure out what exactly is going on with the beam. All right, so let's jump into the easy ones first, and those are the internal forces or the shear and the bending moment. Now, if you guys may remember from statics, the equations for these or the relationships for these are actually done by taking a little slice of the beam and analyzing it. So what I did is I took a beam and I took a little horizontal slice of width dx1, and it's of course subjected to a distributed load Q. Now keep in mind that once we cut a beam open, we release those internal forces. So what I'm going to have first of all is a normal force. So on the left hand side I have my normal force, and on the right hand side I have my normal force plus the change in the normal force over the distance dx1. Similarly, I have a shear force on the left-hand side, and then on the right-hand side, I have my shear force plus the change in the shear force over dx1. And then my final internal force, of course, is going to be that bending moment. So on the left, I have my bending moment m, and on the right, I have my bending moment m plus the change in m over that width dx1. All right, so what we're going to do to start us off is we're going to look at force equilibrium. So of course the easiest one to look at is the sum of the forces in the x2 or the vertical direction. And what we get is we get the shear force V minus V plus the change in V over dx1 plus our distributed load Q multiplied by that distance dx1. And of course, since we're dealing with a static case here, this is all going to be equal to 0. Now it's very easy to see that those v's cancel out, therefore we can cancel the terms and simplify the equation as follows. Now from here it gets even nicer because we see on both sides we have a dx1 term, so I'm going to divide both sides by dx1, and we get the very nice relationship where our distributed load Q is equal to the change in shear with respect to x1. So x1, as we're going to see, that's going to be over the horizontal length of the beam. And that's going to be our first relationship. And again, this is a nice simple one you guys have, I was going to say probably, but maybe most definitely have seen before back in your undergraduate careers. So from here, we have a nice load to shear relationship. Now we're going to take it a step further and consider moment equilibrium. So what I'm going to do is I'm going to take the moment of the same section, so the section didn't change at all, but I'm just going to take the moment around that point A there. Now again, of course, it's in a static case, therefore the moment's going to be equal to 0. So it's very simple. We have a negative moment because of the moment on the left, plus the moment plus the change in moment over dx on the right, minus our shear times the distance dx1, minus our distributed load, which in force form is going to be q times dx, and then multiplied by its moment arm, dx1 divided by 2, and of course everything is going to be equal to 0. As you guys are going to see, we're going to follow a very similar procedure before, where we say, all right, well, we have a moment and we have a negative moment, therefore those are going to cancel. Therefore, we can cancel the terms and simplify the equation as follows. And just like before, we notice that every term now has a dx1 term. Therefore, I'm going to divide all the sides by dx1, and I'm left with the following expression. Now, remember that when we did the shear case doing the sum of the forces, at this point, we had our final expression. But now we have a bit of a problem because we still have a dx1 term left where we have q over 2 times dx1. Now it's important to realize that once we're doing this, what we want to do is gain that exact solution. Therefore, we take the limit as dx1 approaches 0. Remember, we want this slice to be as tiny as possible to obtain an actual relationship. And once we do that, well, that term basically goes to 0. And we're left with the following relationship where a shear is equal to the change in moment over dx1, or simply the derivative of the moment function with respect to x1. Now this is very nice because we have a shear to moment relationship. So again, the load to shear and the shear to moment relationship, you guys have probably seen these before. These are nothing new. But now we're going to take it a step further with everything we've learned thus far into the course. And this is going to start with a displacement function. So when we talked about the strain tensor, we said that the first thing that we need in order to get that strain tensor is going to be a displacement function. All right, so this is where everything kind of comes into play. And this is where you'll start seeing all of those assumptions that we made come into play. So the first thing we say is, all right, we know that we're dealing with a beam. So we have a beam. What we're going to do is we're going to align the x1 and the x2 axis over the length of the beam. So if we look here, x2, that's related to the vertical components of the beam, and x1, that's related to the horizontal component of the beam. Now notice that we also put the x1 axis through the centroid of the beam. As you guys are going to see, that's going to lead to a lot of simplification later on. So we typically place that x1 axis through the centroid of the beam. We do not place it at the bottom of the beam or the top of the beam. It makes it much more easy to place it at the centroid. All right. So now we know that the beam, of course, is going to deflect under the loads, and we're going to get something like this. So that dashed line now, that's the centroid of the beam as it has now been deflected. So what we're going to do is we're going to say that the distance between the x1 axis and the new centroid, that's going to be our displacement function y. So we're just going to, or not specifically our displacement function, but we're going to say that this is the deflection of the beam y. All right, so it goes from the original centroid of the beam to the centroid of the beam after the displacement has occurred. So what we're going to do to derive our equations, we're going to look at 2 points. All right, so we're going to look at the point on the beam before the displacement, and we're going to look at the point on the beam after the displacement. We're going to try and figure out the relationship between the two. So what I'm going to do is I'm going to draw a vertical line going through the point where we first started, and we can start to see a nice relationship between the two. So if we go straight up, we can see that one, the neutral axis doesn't change along this line. The neutral axis at a distance x1 in our original configuration is the same location, horizontal location, as our neutral axis in the other location. But as we can see, because the section has now rotated in the beam, our point has indeed shifted. So we're going to try and figure out what exactly that shift is. What we're going to do is we're going to kind of zoom in on there, And what we can see is we can actually create a nice triangle. So this is where that plane assumptions remain plane assumption comes in handy, because we know that this section is going to be perpendicular to that neutral axis. Therefore, we can create this nice triangle, right? So we know that the point is located at a distance x2 above the beam, and we know that the cross section has rotated by amount of. If we were to look at the horizontal translation due to this, well, it's very simple. It's going to be x2 times sine theta. We have a nice triangle here. It's not too hard to figure out. If we're looking at the vertical component, we see that this is going to be x2 times cosine theta, which again is not too hard to see because of the nice triangle that we have here. Now, the thing that's going to be tricky for some students to realize is from this, we can conclude that our position function, which is small x, is equal to x1 minus x2 times sine theta for the first component. The second component is going to be y plus x2 times cosine of theta. And the third component, which is that in plane component or the in the thickness component, is just going to be x3. Now, if you guys can understand where this comes from, you guys are good to go. The rest is going to be a piece of cake. So what I'm going to do is I'm going to actually bring my mouse in here. You guys usually have not seen my mouse, so here's my mouse, and we're going to try and just show you guys where exactly this comes from. All right, so let's look at this point after deformation and referring to the horizontal direction. So we know that the distance from this axis over here all the way to this dashed line, well, that's a distance x1. We know that, right? Oh, as we can see, our point is actually moved a little bit to the left of x1. So we go from 0 to x1, which is why we have the x1 right here. And then we go back by a magnitude of x2 times sine theta. That's why we have x1 minus x2 times sine theta. If we were to look at the vertical direction, we know that the distance from the original, or from the centroid before deformation, is going to be 0. And we know that the distance from here to the centroid after deformation, so this distance right here, well, that's going to be a distance y. We defined it as y. So that's why we have the y here. But then that leaves us right here. We know that we want to go up by magnitude right here. And we see that magnitude is x2 times cosine theta. So that's why we have the plus x2 times cosine theta. It basically brings us from here all the way to here, so we are good to go. Now, again, in that x3 direction, we have x3, and you guys might be wondering, well, why isn't 0? Well, this is because we're dealing with a position function right now, all right? We're dealing with a position function. What we're after right now is a displacement function. So don't worry about it too much. We'll get to that in a little bit of a second, or a little bit of a second, or we'll get to it soon, basically. You guys know I can't talk when I'm doing these sort of things. But before we get into that, we can realize that there's actually some nice manipulations we can do to our position function. The first one is we assumed small deformations. So what that's going to do is that's going to impact those two terms right there. Because we know if we're assuming small deformations, well, cosine theta, that's approximately equal to 1. And sine of theta, well, that's just approximately equal to theta. Therefore, our position function actually simplifies into x1 minus x2 times just theta, and y plus x2. From here, we can actually start figuring out what our displacement function is. And again, our displacement function u, that's just going to be small x minus big X. Therefore, it's going to be x1 minus x2 times theta minus x1. So if we do that, well, we can easily see that we just get minus x2 times theta. And similarly, for the second component, we have y plus x2 minus x2. That just leaves us with y. And then we have x3 minus x3, which is going to be 0. All right, so there's that 0 many of you guys were expecting. And this is going to be the basis on how we find our strain tensor. So another thing that we notice too is that theta in there, well, we know that the rotation of the cross section that we discussed, that's actually going to be the first derivative of our deflection function with respect to x1. So we're going to make that simplification in the next slide. So when we get to the next slide, again, what are we doing this for? Well, we get displacement functions in order to find strains. So now that we know our displacement function, we can start to find the strains. But the step that we have to do before that is finding that displacement gradient nabla-u. So just to recap, in the last slide we found our displacement function u, which is negative x2 times theta, but we said that theta is the first derivative of the deflection function, and then the second component is simply y, and the third component is going to be 0. From there, we can substitute that into our displacement gradient. I was going to say strain tensor, but we're not there yet. I'm a little premature at that mark, so back it up a bit. We're going to find the displacement gradient, And if we look at the displacement gradients, it's a bunch of partial derivatives with respect to x1, x2, and x3. So if we look at the components of our displacement function, we see that we basically have two components. We have x2, which is very easy to take derivatives with respect to x2 because we know it's x2. But we also got y. Now, if we're taking derivatives of y, we need to know what y is a function of. So if we look at our slides at the previous thing, we can see that as we go across the beam, the deflection is going to change. It makes sense. If I have, let's say, a cantilever beam, the deflection at the support is going to be 0, but the deflection at the end is not going to be equal to 0. So we know that the deflection function changes over the horizontal length of the beam. So therefore, we know that y is a function of x1. Why is this important? Well, if we look at our displacement gradients, every time we have an x1 there, we know that we're going to have to differentiate y with respect to x1. And because so, we can obtain the following displacement gradients, where the first component is going to be negative x2 multiplied by the second derivative of y. The second component in the first row, negative dy over dx1. And then our other only non-zero component occurs in the second row, first column, where we simply have dy divided by dx1. All right, so this is great because now that we have that displacement gradient, we can find our strain tensor. We have a nice formula for our strain tensor, which is simply 1/2 of nabla-u plus the transpose of nabla-u. And as you guys see, we only have one non-zero strain component, which is epsilon 1,1. Now, if we look at this and we were to ask you guys, what is epsilon 1,1? Well, it's simply going to be negative x2 multiplied by the second derivative of our deflection function. All right? And since x1 is constant over the cross section, we can see that this strain profile is actually going to be nice and linear, which is perfect. We want something that's nice and linear, it's nice and simple. And if you guys have ever designed any sort of steel or designed any sort of concrete, and you guys were to do a sectional analysis, we always assume that the strain profile is linear. So this is exactly where it comes from. All right. So now we said that from constitutive laws, if we know the strains, we can actually figure out what the stresses are. So from the from the strain tensor, it's easy to see that there is going to be a stress component sigma 1,1. Makes sense. If we have a non-zero epsilon 1,1, well, there must be a non-zero sigma 1,1. So from our constitutive laws, while ignoring Poisson effects, we can determine sigma 1,1 as simply Hooke's law, or sigma 1,1 is going to be the Young's modulus multiplied by epsilon 1,1. From here, we can say, well, we know what epsilon 1,1 is. We just derived it on the previous page. Therefore, sigma 1,1 is going to be our Young's modulus E multiplied by negative x2 times the second derivative of that deflection function. Now, you guys may not see where this next step comes from, but it'll be shown in later slides. We can actually simplify this a little bit more, where sigma 1,1, or stress component 1,1, is going to be negative times the moment function multiplied by x2 divided by the moment of inertia I. So again, this will be shown later, or how we go from the second step to the third step, so don't worry about it too much. All you guys need to know is that if you guys are calculating stresses in beams, this is the formula we typically use, and you guys have actually probably already seen this before in mechanics of materials, right? So another thing that we also have to discuss is, although the strain tensor has no shear component, so epsilon 1,2 we found was 0, well, we know that there actually is going to be a shear stress component, even though there is no shear strain component. Why is this? Well, we know that our beam is subjected to a shear force function, V. And if we have a shear force function, well, then of course there must be some shear stresses. However, we go back to mechanics of materials, and we know that we actually have a very nice equation that gives us the shear stress, where sigma 1,2 is equal to negative VQ divided by I times B. So it looks really crazy, but the components are really simple. V is going to be our shear force function. You guys already know what that is. I at the bottom, that's our moment of inertia of the beam. Again, very simple. B, that is the thickness of the beam into that thickness direction, or the E3 direction. The only thing that you guys might not know is that Q. So Q is the first moment of area, which is a double integral. It's not too bad. But since we have aligned our x1 axis through the centroid of the beam, we can actually simplify Q into one nice equation, where Q is equal to B times T over 2 minus x2, so that T, that's the height of the beam, and then multiplied by T over 4 plus x2 divided by 2. So even though it looks pretty gross, it's very easy to calculate. You guys won't have trouble with that at all. From there, we can move on to a moment-deflection relationship, all right? So this is where everything is going to start coming together by this moment-deflection relationship. Now, from the cross-section, or the stresses on the cross-section, we can actually determine what the moment is, where the moment is equal to the double integral of negative sigma 1 times x2, and then integrated over the cross-section. So integrated over dx2 and dx3. Now we say, all right, well, if we look at sigma 1 on the previous slide, we figured out what exactly sigma 1 is equal to, where it's equal to negative e times x2 times the second derivative of our deflection function. All right, and then we can also realize that we're integrating over the cross section. So we're integrating with respect to x2 and with respect to x3. The Young's modulus e, well, that is not a function of x2 or x3, therefore that's going to be constant. If we look at our deflection function, which is y, we said that that's a function of x1. Therefore, that's also not going to change over the integral. Therefore, we can bring out those two outside of the integral because they're going to be constants. Therefore, m is actually equal to e, the Young's modulus, times the second derivative of our deflection function, times the double integral of x2 squared with respect to dx2 and dx3. Now, for the mega nerds in the chat, they're going to go, oh my gosh, I know what that double integral is equal to, where the double integral of x2 squared with respect to x2 and x3, that's actually equal to the moment of inertia I. Therefore, we can actually have a nice relationship between our moment and deflection, where our moment m is equal to ei, which is commonly referred to as the flexural rigidity, which is simply the Young's modulus multiplied by the moment of inertia, and then multiplied by the second derivative of our deflection function. Now we can take it a step further because we actually have nice relationships between load and shear and moment that we derived at the beginning of this lecture. Therefore, we know that Q, our distributed load, is equal to the derivative of shear, which is then equal to the second derivative of moment, which is then equal to the second derivative of the expression we just obtained. Therefore, we can create a relationship between the distributed load as well as our deflection function, where Q is equal to EI times the fourth derivative of our deflection function. Why is this important, and why did we go down this road? Well, if we're designing a beam, if you guys are designers in an office and they give you a beam, the first thing that they will always give you is what are the loads on the beam, aka what is Q. So if we look at this equation, we know what Q is. We almost always know what EI is, so that's not going to be a problem. Our only unknown now is going to be that deflection function. Therefore, we can solve for that deflection function. So when we're dealing with an Euler-Bernoulli beam and we're trying to do an analysis of it, it's actually basically broken down into 3 steps. The first one, of course, is going to be what is that deflection function? Well, we go to that equation we just derived, where Q is equal to EI times the fourth derivative of the deflection function. We know what EI is, we know what Q is, we can solve for that deflection function Y. And once we know Y, everything else kind of opens up to us. So the next thing I like to do is we can say, all right, well, we can determine the shear and the bending and moment functions from that deflection function. Since m is equal to EI times the second derivative of the deflection function, well, we know EI, we now know what that deflection function is, we can solve for m. Same thing for the shear function. V is equal to EI times the third derivative of the deflection function. Again, we know everything except for V. We can very easily solve for V. Now the key here is these two functions, both the shear and the bending moment, they're going to be functions solely of x1. So they're just going to change along the horizontal length of the beam. They won't change over the vertical span of the beam. All right. And from here, we can take it a step further, and we can now find the stress components from the moment and shear functions. Remember that our equation for sigma 1 is negative m times x2 divided by I. x2, that's just going to be x2. I is the moment of inertia, which we know, and m is the moment function, which we now know. So we can easily determine what sigma 1 is. And the same thing for sigma 12, where it's equal to negative vq divided by ib. V, that's our shear function from above, which we know. Q is calculated from the cross section, which we know. I is the moment of inertia, and B is that in plane thickness or into the page thickness. So therefore, we know everything over here. The only thing that I want you guys to remember when we're dealing with these stress components is they're functions of both x1 and x2. So they're going to change over the length of the beam as well as over the height of the beam. And this makes sense because if we're dealing with the beam under flexure, we know that it's compression at the top, tension at the bottom. Well, this is why x2 comes into play. So if we're moving near the top of the beam, we know it's going to be under compression. Therefore, sigma 1, it's going to be negative. However, if we're moving towards the bottom of the beam, we know it's going to be under tension. Therefore, sigma 1,1 turns into a positive value. So that's it for Euler-Bernoulli beams. I hope I was able to help. Now, it can also be a little bit confusing, these steps, so I've also prepared an example using the program Mathematica. So if you guys want a little bit extra information on how exactly we execute these steps, please refer to the example in the description below. But yeah, that's it for the lecture, guys. Thank you guys so much for listening. I will see you guys in the next lecture video.